Thank you all for staying up in the middle of the night to hear this. Okay, I am Ben. I've worked with machine learning since the old days, the last millennium, even before 1990. Mostly working on speech recognition back then, and more recently on language modeling and language understanding. I've worked in Japan and in California. Japan was mostly at Panasonic and a small company called ATR. And Panasonic, I think you all know, they make outside of the US, they use the trade name National. So if you're overseas, you probably know it as National. Then I came back to California and I worked at Nuance Communications. We did speech recognition for telephone things. And more recently at Toyota Info Technology Center, and where we worked on various things for use in the car, mostly speech interfaces for the car. And currently I am at Metabob as Director of AI. Okay, first, I'm going to talk about topic modeling today. I want to begin with why we're doing it, what's it good for, and then get into the how, the algorithm, how it actually works. I'll talk about it more conceptually. I'll give you code at the end. We also want to talk about whose module shall we use. There are several different Python implementations of topic modeling, and I'll talk about the benefits and drawbacks of each one. And finally, I'll get into what the problems are. There's always problems. Don't tell me there's no problems. There's always problems. And one of the biggest ones is getting a lot of data. And dealing with these problems takes most of the time, actually. So first of all, what is topic modeling? What are we doing here? An early application of topic modeling is spam filtering. So, you get an email, a lot of them are spam. You can spot it right away. It has words like free, now, lottery, car insurance, newspaper subscriptions that you don't want. So you can spot common words like that. And the output of this topic modeling is the probability of spam. So you feed it in a document, your document is your email, and you get out a number between 0 and 1. If it's 0, it's probably not spam. If it's 1, it definitely is spam. And the other output of course, is 1 minus p, which is the probability that it is not spam, which is sometimes called ham. But I think that's old too. A newer application of topic modeling, as if you're a Gmail user, you have seen this for several years already. You split the mail into several different categories. There's spam, there's junk, there's social, like Facebook stuff, there's promotional things. You can also have categories like phishing, and an even earlier usage of topic modeling was to detect hate speech. For example, if you had a news website and they show you a news article, and then there's a discussion link at the bottom so you can discuss it. This is before Facebook was very popular for this kind of thing, Facebook and Twitter. It was often on the news website. And the problem with there is that people would start inserting hate speech, especially if it's maybe a politically sensitive article. So of course, no newspaper publisher wants to be hosting any hate speech. So you got to detect that too. So topic modeling has become more important in recent years. Our application is not spam or hate speech. Our application is just for detecting what a GitHub commit message is. So you're all familiar with GitHub, I think. And below here, I don't know if you can see my cursor on here. I don't think you can. Well, anyway, underlined in red there is a typical GitHub commit message, which you can see in this case, it seems to be about documentation, right? I don't think it's about security. I don't think it's a bug fix. It's about documentation. So that's what our current application is. That's what we're trying to do. And here's what you typically get in a topic model. This is actually a pretty good topic model. You get a topic number and the terms in it. So for example, at the top, topic number 54, They don't come out in order. They come out in all kinds of random orders. Model TensorFlow GPU training and train. So obviously they're talking something about using GPUs to speed up the training of a TensorFlow model. TensorFlow is a module that is often used for neural networks. It's very GPU intensive. And the next one, number 30, submit unit step checklist document. I think they're talking about testing, probably unit testing. There's a checklist and there's some steps. So it looks like it's about testing. Number 68 seems to be about legal stuff. A CLA is a contributor license agreement. It's a something you fill out if you use some code that you didn't develop your own. And sometimes the contributor of the outside code needs to have you sign a license agreement with them. So that's an example. That's a kind of a legal thing. And you can see each of these is about a thing. Now, number 5 is interesting because it's also about testing, I think, or it could be about support because it's talking about a ticket. Not exactly sure. It could be a combination of two, but looks like it's about testing. Number 40, it's a little bit hard to see. It's got several things in there, and sometimes you get that problem. Anyway, so you see what's going on. The topic model comes out here. I want to look at the last 3 are interesting. Number 66, character long environment white space 79. That's a bad topic because it's got number in there. You really shouldn't have a number. All those numbers should be translated to number because we don't care about the specific number 79. That doesn't have a particular meaning. It should be done like number 33. They're talking about translating. Maybe they're translating a document, or maybe they're making sure their code works in a place with different languages. We don't really care what the language is. We want to know that it's about language translation. We don't care if they're talking about English, Chinese, Japanese, German, whatever. We don't care what the language is. That doesn't tell us anything about our topic. And also number 38 is a really common problem. You don't want to train on everybody's email addresses. That'll be too many individual things to train on. You just want to transform any email address to email. So that's an example. Number 33, 38, and 66 are examples of topics that if you see that in your topic model, you need to look at some stuff. And I'll talk about that a little more in the presentation later. So how do you do topic modeling? There are many ways. The easiest way is what's called a unigram. TF-IDF is a variation of that. Unigram is basically spotting common words, okay? Like I described in the spam. If you see the word free and now a lot, then you increase the probability that it is spam. You got some problems though, because what if you have a document talking about Apple? Is it talking about the company? Or is it talking about fruits? Okay. Also, and when you get into a lot of documents, you have a lot of words, and Unigram is going to fail you because there are certain words that are just common all over the place, like the, okay? So what you want to work on, there's a variation of a unigram type called TF-IDF, term frequency, inverse document frequency. Basically, it is, the formula for it is shown on the right there. It basically, your term frequency is how often the word appears in that document. And the document frequency is how many documents have that word. So if a lot of documents have that word, like the word the, you should put that on the denominator and say, no. You got to normalize this. You got to decrease that because the is all over the place. Okay. But if you have a word that's very rare, that only occurs in a few documents, and you have it in this document, well, that means it's a very important word. Okay, so that's what TF-IDF is doing. Another one is LDA, called Latent Dirichlet Allocation. It was developed by somebody named David Bly. He's at Columbia University. This actually matches pretty well the kind of data that we have. You're basically trying to find the topics underlying. Latent, by the way, means hidden. It means you can't see them. So you got these documents and they got topics, and nobody's showing me what the topics are. It's my job to get the topics. And that's what LDA does. It's finding the hidden topics in that data. And it can accept partially labeled data, which is really nice because we have a lot of data, some of which is labeled, some is not. Typical early experiments on these had about 20,000 to 70,000 docs, and they're trying to extract 100 topics out. That's rather similar to what we're doing, about the same amount of data. We have more actually when we're trying to get fewer topics, which means our problem should be a little bit easier. And to the right, that's basically the form. I won't go into the detail, but that's the basic formula on which LDA is measured. You're trying to maximize P of theta ZW given alpha and beta. That is, you're trying to maximize the probability for each document you get in. You're trying to maximize, you're trying to find the topic with the maximum probability. Again, I'll get into that a little bit later. Another one is called neural topic modeling, NTM. It's newer. Amazon SageMaker provides it. It needs a lot of data and it needs a lot of GPU power. The architecture is a little like an autoencoder, and autoencoders are used a lot for image compression, speech compression. So I have a little diagram of an autoencoder on the right. What you do is you feed it a lot of images in the blue, okay? So each box in the blue is a pixel, okay? And then the green is a hidden layer in the neural network. And then it comes to 3 red values. So you're trying to encode this picture with 3 red values, okay? And then on the other side, you have a neural network, and then it outputs a bunch of pixels, okay? And you want those pixels on the right to create the same image as what you got on the left. Well, of course, you're going to get a little bit different image because it was reduced to 3. So what you do there, this is an autoencoder, can be used for many different things. You present a lot of pictures to the front and you try to generate the same picture on the back. So you have a measure of how different the picture is, how many pixels are wrong. You train this network on all of those pictures. It could be audio, it could be pictures, it could be text, it could be anything. And then what you do is so what's going on is basically the green part becomes an encoder and the green part on the right becomes a decoder. And you have a really nice, very optimized encoding scheme. So you got an image on the left, you're representing it by only 3 pixels or by only 3 numbers, and you get the image out on the right. Well, of course, you know, it's never going to be perfect because of compression. And this is a ridiculous example of the Mona Lisa being reconstituted with a few defects. Another type of neural network-based model that can be used for topic modeling is a sequence-to-sequence. It really needs a lot of labeled data, and the best way to implement this is using Python modules Keras or PyTorch or TensorFlow. There are many more different types, but it always needs more data. So we have chosen to do LDA because it matches what we're doing a little the best. So here's basically what's going on with LDA. Okay, the assumption is here's a document. Okay, and the assumption is that there's a certain number of topics, K. In this case, K equals 4, that exist for the whole collection. The topic is the distribution over words that is shown by T. So you see for each topic, you got some words in there and each of the words has a probability. So that's a distribution. It is actually, you know, there are normal distributions, there are Poisson distributions. This one is called a Dirichlet distribution. So the way you generate a document, assuming that you have the topics extracted, the way you generate a topic, the way you generate a document, this is the LDA assumption, is that you choose a distribution over the topics, that's shown as number 1, and for each word in the document, you choose a topic assignment, number 2, and choose the word from that corresponding topic. So you can see this document, it says how many genes, okay? Genes comes from yellow, and it's pretty high up there. So that means it's likely there's a piece of evidence that this is the yellow topic. But there's some evidence that it's the red topic too, which is organism. And there's some more evidence that it's the red topic too. And then you go down, you see some yellow ones and you see some red ones and the blue ones, okay? And it turns out the number of colors you see, yellow is predominant. So we would say that this document is primarily the yellow topic. In other words, it's mostly about genetics. If we said it was mostly about the red topic, that's probably about evolution. If it's mostly about the green topic, that's about brain and neurons and, you know, brain science. If it's mostly blue, it's more about computing stuff. So that's the basic assumption of what LDA is doing. And here's the guy who basically invented that algorithm, a guy named David Bly. He's at Columbia University. And in words, what are we doing here? We're assigning words to topics that each topic contains words that often appear together. That's called coherence. So for example, united, united will often appear with the word America. Not always. You could talk about UPS, some other thing. Basketball often appears with win. It also appears with lose. It also appears with certain team names too. And you're going to assign words to topics according to these two constraints. In each document, you want to allocate its word to a few topics. In each topic, you want to assign high probability to a few terms, okay? These two constraints are opposing each other, because if you only do number one, sure, I can just allocate all the words to one topic. There you go. You're done, right? You only have one topic. All the words are in there. Well, that's no good, because you violate number two, which is in each topic, you don't want to have too many terms. So that's another description of what LDA is doing. What winds up happening there is, here's a graphical representation of what's going on. The yellow here on the left is, each yellow dot is a topic. This is an application where you have only 3 topics, and the topics are sports, science, and politics. And they're classifying a bunch of newspaper articles. Each newspaper article is in yellow. And this is nice because it looks like those newspaper articles came from a paper which has it very well divided. The article about politics is really about politics. It's not about sports or science at all. But you don't want to have too many articles in the middle. That's kind of hard, but sometimes you do. Too bad, you just do. Anyway, this is graphically what's going on in the LDA algorithm. And on the right here, here's the generative part. So you have these topics now. You have the green topic is shown up at the top here, politics. It's very close to the word referendum. So let's say you have the words referendum, planet, galaxy, and ball in your document. You're going to choose one of these topics. Is probably going to be green. It's very close to what you have. That's the highest one. And putting them together, that's how the LDA works. So we're going to rewrite this in Python, right? No way. It would be slow and it would be full of errors. What we want to do is we want to use a module that somebody else has already made to do all this stuff. And fortunately, this LDA algorithm is popular enough that there are some good modules to do it. The modules with the largest user base are GenSim and Tomotopy. And as I described here, GenSim, it's older. It's been around longer. Its basic developer is Radim Rehrik. I don't know if I'm pronouncing his name correctly, but I think that's right. It's mature. It has a large user community. It's very well debugged. It's a very active user community. A lot of people all over the world are using GenSim. Tomotopy is newer, but it uses something called Gibbs sampling. That's a detail in there, which I won't get into now, but how it estimates these probabilities is different. It uses something called Gibbs sampling, and that's better for short documents. And that's what we got. We don't have long, you saw our data that we had there before. We have like GitHub comments, right? GitHub commit messages. They're pretty short. They're like 10 or 20 words at most. We're not doing newspaper articles. Those are long. So GenSim may be better for newspaper articles, Wikipedia articles, long things on the web. But Tomotopy is better for shorter things. And, you know, it'd be better if we had longer, but that's what we have. That's our data. So we're using Tomotopy. Also, I ran both of them. I looked at the topic model output, and Tomotopy just looked better. GenSim had kind of nonsensical words all over the place. Another nice thing about Tomotopy is it runs faster, but in fact, it doesn't run faster. It trains faster. But if you look at the runtime, it runs slower. As you know, for any machine learning model, you have training and running, right? You really want it to run fast if you want it to use it in real time, but training slow is okay because you're usually training on your own machine, your own servers. You can throw a lot of extra CPU power at it. But unfortunately, Tomotopy, it trains a lot faster, but it runs a bit slower. I wouldn't say horribly slower, but you know, their documentation says it's faster, but I measured it to be a little slower. I will say this though, Tomotopy is easier to parallelize than GenSim. So if you're running over a lot of documents at one time, Tomotopy is faster depending on how many CPU cores you have. Unfortunately, these are not very well helped by GPU. So you want some code? You got some code. Here's how you use it. Okay. So first of all, first of all, you have to read all the data. So line number 7, I'm getting them into a list of strings. So all the documents come into a list of strings. And number 7, I should have said train file names instead of input file names. Okay. And so number 10, I'm splitting them into tokens. So I'm just splitting them into individual words. It's a simple, stupid tokenizer. I'm going to get more into the tokenizer later. But for now, I'm focusing on the actual language modeling. And part 3, which is lines 13 to 17, that's where you're actually training the model. And you can see that there's a few parameters here, which you have to play with to see what's good. And it really depends on the data that you have. In my case, I'm trying to extract 100 topics here, and I'm going to remove the top 100 most common words because I don't want words like the and to and I and be and have and, you know, a. I don't want those in my topic model. I really want to get rid of those. So I want to remove the 100 most common words over the whole set. I also am using min-df. That is the number of documents that it appears in. If it appears in only one document, it's pretty likely a spelling error or it's such a rare term that we can't really make a topic model from it. I think min-df should be higher than 1, but for now, I just put it 1. Unfortunately, Tomotopy defaults to 0 there, which is kind of dumb. But I just set it to 1, and we're still experimenting with which are the better parameters. Okay, so now we've trained, now we have initialized the model to train. We have not started training it. At line number 15, we're adding the data to the training set. That's making the corpus. Okay, so a token list, you know, you're adding many tokens. So you have a list of tokens. Actually, as a list of strings is what it is, because each token is a string. And now at line number 16, you actually do the training. This takes the most time. And this one, you have to play with the numbers. For each document, I'm training it 100 times. And then I'm going over that 10 times. Okay, that's 10 up to 1,000. So each document is presented 1,000 times total. Okay. Again, you have to play with those numbers or else you overtrain your model. But you have to play with those numbers in line 16. And finally, at line number 17, I write out a summary of the model. And that's what you saw. That's what you saw on this slide back here. This is a summary of the model. So that's what I'm doing at line 17. And so now I've trained my model, trained the topic model. Now, of course, what you need to do is you got a new document. What topic is it? And that's what's going on in lines 20 to 24. Okay. So you get the tokens from the new document. And by the way, this does not care about the order of the tokens. It's what's called a bag of words model. So it's just taking the tokens. And then line 21 and 22, you have to do this twice. You actually, without getting into the detail too much, 21 does all of the work about finding. It does all the work that you saw in this early graphic. It does this work. It's doing all of this. This is done in line number 21. So it figures out what words from what topics were in that document. And line number 22 says, okay, now what topics were they? Okay, and it outputs a topic distribution. And that is basically just a bunch of floating numbers like 0.2, 0.1, 0.9. Oh, I describe it on the right here. Yeah, it's just like this. It's, I wonder if I can get my pointer to show. Pointer options. Hey, look at that. Maybe this will work. Here. That's what topic dist outputs. It outputs, some floating point numbers. They should all add up to 1. This is a stupid example. It doesn't, but they'll all add up to 1. And basically the one with the highest number is your topic. So 0, 1, 2, 3. In this case, it was topic number 3 was the winner. Okay. And then you type it out here. The best topic was topic number 3 because topic number 3 had the highest number. So that's basically how LDA works. That's how we do it. Now that's very simple. Of course, it's not all that simple because it's got a lot of problems. Okay. Biggest problem is the data source. If we just use the, you guys, you're familiar with GitHub and doing your comments. Where the heck did my cursor go? Here it is. Okay. This is the kind of data that we get. And you know what your commit messages look like. At first, it's a really nice commit message. And then another nice commit message. And then you get a little bit less specific. And then, you start getting lazy. And then you start getting lazy and getting really, really lazy. And this is what actually happens. You get these, and we see strings like that, like, this is not an English word here, I mean, yeah. So anyway, this is the reality. So we get data like that. So what we've done is we're not using only the commit message. We're using some other things. For example, you can report an issue. A user of the software can report an issue. And then the developers start talking to each other about maybe other people have the issue. They start talking about what that does, what's the effect, and then how to fix it. So those are a lot more useful than these commit messages. Okay. Another thing that is a problem is not only with LDA, it's with anything, is choosing the hyperparameters. And by that, I don't only mean the number 100 and 1,000. Those were the number of epochs and the number of iterations. There's also the alpha and the beta and the number of topics. When you run LDA, you have to tell it the number of topics at first. And alpha and beta have to do with the distribution in those triangles. I'll go back there and show you, but you see how the yellow documents are pretty close to the topics, right? That's a low alpha. I need to know whether my input data is like this or if it's more clumped, towards the middle, right? If my topics are all kind of located around here, I should choose a high alpha. If they're more out like there, like it is here, then my alpha should be low. And the same with beta. Beta is the same, but for this side. Okay. So you gotta play with those parameters. Let's see. Word order is ignored. I think I mentioned that before, but that's one of the criticisms of LDA is that it doesn't look at the order of the words at all. I would argue that that really doesn't matter, because for English, word order is really important, but for some languages, word order is not important at all. And some people just, sometimes you don't care about the word order. You just put in the words. So for getting the topics, it really, if the word order, sometimes the word order is important, like pull request. I'm doing a pull request. I want to request you to pull something. That's different. So pull request is a special word. So that, for that, we use something called bigrams. I won't go into too much detail, but basically if you see two words together frequently, you combine that into one word and call it a pull request, not a pull space request. And you can do trigrams too, you know, sequences of 3 words that go together frequently, but we don't have, maybe we do have enough data, but I don't think that helps us very much. We're not doing anything that has a triplet of words a lot. We do have bigrams though. Now, the next thing is you're going to tune all these parameters, right? How do you know what parameter set is best? What do you know? I mean, 0.01, 0.1, what should we take? Okay. I tend to like to evaluate things by accuracy, but in order to evaluate by accuracy, you need to have some labeled data. We do have some labeled data, so we can see what topic the topic model comes out with. It says topic number 7, it was about documentation. And we have a label, you know, we had human labelers who said this is about documentation. You're gonna say, hey, that's right. One of the problems with that is that the topics that come out aren't really well labeled. They're just, you know, you saw those sequences of words. So you got to assign a topic name to that sequence of words. And that has to be done by human. Anyway, that's one way to do it, accuracy. A good way to do accuracy is to have a very low number, have a low K. And if K is low, then you can measure accuracy somewhat. But if you have 100, you know, if you just miss a little bit, you know, it's considered a wrong result. So accuracy turns out to be not as useful as I'd hoped. This is the best way, eyeball. That means by just having a human look at it. That's real time consuming, but that's really the only fail safe way. Unfortunately, it's slow and expensive and time consuming, but we are doing this because it's the best way. Another way is by coherence, and coherence is something we're looking into, and it seems to do very well. It's a score that you can calculate, so you don't need, well, basically what you want is you want to have a score that that correlates well with human observation, right? Okay. And coherence is that one. Coherence is basically measuring how many words appear together in the document. Okay, so you want documents with words that appear together, as I described in an earlier slide. Coherence is a score that measures that. There are several different ways to calculate the coherence. We use something called CV, and it does not mean cross-validation. It's weight, and it's not the same as correlation. It's coherence. It's basically how many word pairs are appearing together for documents that have the same topic. And if it's high, that means you did a good job. If it's low, that means you didn't do a good job. Try some other parameters. Unfortunately, it doesn't correlate perfectly, but it's something that we can calculate, so we don't need so many hand labels. The other thing that you need to do, of course, as with anything like this, is you need to do a lot of data cleanup. I'll get into that in a minute. I mean, it's described here a little bit, you know, I mean, we really can't use these. Here, have some code. That's really not useful for us. Bug fixes is useful. This is marginally useful, and this is junk. Okay. So for example, here, the word hands and that's not English. You can't use that. So anyway, there's a lot of data cleanup to do. And it's not only that, that's kind of a joke, but I'll show you in the next slide a bit more about data cleanup. And you saw in my code, we're tokenizing by just splitting the input into words. That's actually a really dumb way to do tokenizing. You really have to do a smarter way of tokenizing. Again, next slide, I'll get into it. And there are modules to do the tokenizing for you. One of them is NLTK. That's been used for a long time. There's another one called Spacey. They're on version 3 now. That seems to be the best one. So I'll go into solving some of these problems now. First of all, the most important and the one that everybody knows about is data cleanup. Here's the actual data. This is not a joke. This is real data that we get in. Okay, here's a nice one. Okay, bump the version up to 1.1. And when I say crappy, I should say simple. A simple tokenizer will just split the words. That's nice. That worked pretty well. Now here's another comment that we get. We got an emoji. We got the word it's. And it's just going to split them. Here's an emoji. The emoji comes into the topic model. That's not good. The emoji should not remain. And it splits everything. Here's the word it's. That's really 2 words. It's not 1 word. It is. And here's a very common word, but it's okay. It's doing it right. And then here's something we get too. We got a lot of foreign language input. Unfortunately, we can only do 1 language at a time, and most of the comments are in English. So we have to filter out all. By the way, if anybody has a question, I hope you're asking because I'm not hearing. But I'll have questions. Yeah. Sorry.
There's one question in the chat. I mean, I figured we
there was. I'm sorry. I'm not able to see the chat when I'm sharing full screen like this.
I mean, I figured
that's not true.
We can share it at the end.
Oh, TF-IDF. Okay, I will explain that at the end. I will explain it at the end. The reason I'm going to do that is we don't use TF-IDF, so I really haven't looked at it very much, but I'll explain. TF-IDF means term frequency inverse document frequency. That's what it means. That's what it means, and I'll do more explanation on that later. Yeah, so we want to filter out all the non-English. So in this example, there's some Chinese stuff. Sometimes you get German words with umlauts and so on, which are very rare in English, although you can have a double dot over the word naive, but it's rare. So in this case, this is the real simple tokenizer. It took them out as separate words, and it's going to train a topic model using those words, which is, of course, inappropriate because there's a lot of separate words in there, right? Know Chinese well enough to read, but I know this means this is an example of a word that you would want to take out because it means 1. Okay, so without cleanup, if you don't clean up the data, you're going to get a topic model that looks a little like this, and you can see. I mean, this has got some junk in it. It's got the first one is actually okay. But the other one, it's got it's got some HTML in there, right? And then it's got a little piece of HTML in there. This has some HTML comments in there. Those don't belong in the topic model. The topic model should be meaningful words only, okay? Not like a triple comment stuff. This is an interesting one, fixed. Okay, fix and fixed actually refer to the same thing. So it's not very good to have the word fixed in there. You want to have the word fix. So I will fix, or I did fix, or I fixed it, should all map to the same word. I'll get into that in a moment. Readme.md is kind of okay. So this is okay. It's not too horrible. This is actually fine. But the point is, you're going to get some topics like this and this that's got junk in them. And that's not really helping you at all. Those are junk topics. Those are meaningless. So at least what we need to do is remove stop verbs that are really, really common. And for example, I and is and the and I and not and thanks. So that's something pretty easy to do in data cleanup. Okay. Another thing is, delete non-English, and then the next is tokenizing and lemmatizing. So I'm going to get into this a little bit next, and I won't go too far. We're actually, believe it or not, we're near the end. I promise you, because I've done most of the stuff about the model already. So let me get into tokenizing just a little bit. And you can see this is a bottomless pit. You can spend the rest of your life working on tokenizing and lemmatizing. Here's an example of something we need to do. A simple tokenizer will just split I'd agree to do into these 3 words. or in these 4 words, okay? That's not one. That's not good because I'd is actually I had. So it really should be split into 2. And had is a really kind of a common word, so that should be taken out. Agreed is okay, we can leave that. To is a pretty common word, so let's get rid of it. Do, that's a verb, that's good, that's an infinitive, that's good, keep it. Do, done, did, they should all map to do, that's fine. Okay, so I agreed do is what this really should map to, okay? We also need to do lemmatizing. This is the, this gets very grammatical. This is a little hard. For example, I showed you the word agreed. It really should be present tense because if somebody said, I will agree to do that, that's the same meaning is I agreed to do that. Okay, that's basically somebody is saying an intent that he's going to do something. Okay, so that's basically the same meaning. So we really shouldn't keep details like tense and plural and so on. We got to put them down to a root form. There's something called stemming and lemmatizing. Stemming is a simple way to do it, which just takes the word fixed and changes it to fix. That's a really simple way, and it works for a lot of English words, but not very well, because then you're going to have, I caught the error. I think I can catch the error. You really want to have the word catch, and stemming won't do that. Lemmatizing will. So lemmatizing, you need full lemmatizing. And to do lemmatizing properly, you really need the software that kind of understands the details of the language, okay? You also really want to do tokenizing and lemmatizing together because, for example, I'd, that could be I had, it could be I would. Both of those are I''D, right? So you need something that understands the grammatical structure well enough to say that I'd was I had, and you're going to lematize it to I have, okay? And you're also going to delete it because have is really common, but that's separate. You also have I would, but you got to translate the I will. That's also really common. So this is not a great example, but you get the point is you really need to do tokenizing and lemmatizing together. And it gets really, without going into detail right now, you can see it can get really confusing. Which one do you do first? You do the tokenizing first, you do the lemmatizing first. You really need to do it together. NLTK does them in sequence like that. Spacy does them together. And Spacy is an incredibly useful module. And it's developed by these two, Ines Montani and Matthew Hannibal, and several others. I don't know the others, but these seem to be the ones that are often associated with it. So now what we can do is remember the simple tokenizer we had in the previous code. We actually, Spacy is so elegant. You can do this. This 4 lines will make a much better tokenizer. You load its model. It has a model with all kinds of rules, and actually it's a transformer-based neural network model. It has some trained aspect and it has some rule-based aspect. And then here's your tokenizer. So this code can be just dropped in the previous code, and you now have a much better tokenizer. And now your front end will make much better results. It'll say bump version to 1.1. It will translate into a number. 1.1 looks like a version number to me. And it'll get rid of emojis because that's an out of vocabulary word. It's not an English word. It'll take its, it'll expand it to it is, it'll expand it to it be, and it'll say, okay, that may be a stop word. So we're going to get rid of it actually. And the is a stop word also. It's a really common word. So we're going to get rid of the word stop. And you can see it got only the important meaningful words. That's what Spacy helps you do. Okay. It also, it has a little trouble with Chinese. So it actually, we had to do some extra code to get rid of this problem. But let me see, how should I explain this? Spacy can help with this problem on line number 4, but it's not perfect. There's also sometimes you misspell something. So there's additional code you have to do. But basically, Spacey does a really good job of all of these data cleanup kind of things that you have to do. Okay. Now, are we there yet? Have we done everything we need to do? We got this like 20, 25 line program that does everything. Okay. Well, first of all, no. First of all this stuff with Spacey, there's a lot of settings to do, right? For example, well, okay, here are the most important things that we need to do, okay? We need to get more data. Any machine learning, language model, speech model, image recognition, you always want more data. You also want relevant data. Unfortunately, transfer learning does not work well for the LDA type of model. If you want to evaluate better, you need to get the label data. That's also really important because if you get labeled data, you can use a more sophisticated model. We don't have that much labeled data. It's very time intensive to get. So we have some, and we're expanding a lot. But if we have more labeled data, then we can do a better job of evaluating our system. And we can also enable supervised learning. And that is like the sequence-to-sequence network and more sophisticated models we can use, okay? Another thing to do is try transfer learning. As I mentioned, transfer learning is a technique that's often used for various type of neural networks. It's very powerful because you can use data from a different application and you train your model based on that data, which is for, instead of detecting topics, you could just be detecting something else. Okay. For example, we could get a lot of data from a newspaper or from Wikipedia. This is a common thing to do. You get a lot of data from Wikipedia. You already know what the article is about. We know this article is about politics. We know but this article about sports, and we know this article is about something else, right? So that's labeled data. So we can train a really good topic model based on Wikipedia data because it's labeled. We already know what it is. And then what you do is you change some parameters and then you add your real data for your current application and you change the outputs a little bit. Okay. And you change your learning parameter. That's a common technique for neural network based models. Unfortunately for LDA models, we've tried it and it didn't work at all. It was terrible. If we use a neural network based model, I think we may be able to try transfer learning, but for now that didn't work. And the other thing, if you get more labeled data and just more data, you can try more sophisticated models like the NTM and the sequence-to-sequence models. They just require a lot more. With more data, you can get a better model. And if you want to learn more about Tomotopy and Spacey, here are some resources. This is the API documentation for Tomotopy. It stands for Topic Modeling Toolkit in Python, so you don't have to remember it's not tomatoes. It's the documentation is in English and Korean. Korean seems to be updated before the English is. The one nice thing about Tomotopy is there's a lot of variations of LDA that it can do. It can do LLDA is labeled LDA, so all of your data is labeled. You can make a better model that way. PLDA is a partially labeled LDA. So the idea is that part of your data is labeled. Now, the weird thing is this describes our data and we tried it and it gave us really crappy results. So I don't know about the PLDA. HLDA is something called hierarchical LDA. So you saw that sometimes it got two topics which were really similar to each other. That means those topics could maybe be blended into one. So instead of extracting 100 topics, I could do 99 topics, right? HLDA lets you do that. It's called hierarchical LDA. So, it will say, okay, I'll extract it into 100. And it looks like these can be collapsed and then it will extract it to fewer topics. And that's actually useful. It's really nice to have it go into fewer topics because they'll be clustered better. And for Spacey, here's the page about Spacey. It's a lot more complicated to use. So it's not, Tomotopy is actually really simple to use, a really nice, clean API. but Spacey is harder to use, but it's so much more powerful. And they're supporting, I think they're supporting like 45 languages now. So this is very language specific. So Spacey is incredible help. That really makes the difference between getting a useful topic model and nothing. And that's pretty much, I hope I didn't blow you all away, but that's pretty much the end of the presentation here. I'll get back to your, I see one question about TF-IDF. I'll go back to TF-IDF. It's a very simple one. Here it is. Yeah, here's TF-IDF. It's term frequency inverse document frequency. It basically tells you what the important terms are. It doesn't actually extract topics. It just, you have a document collection and you put in a new document and it will tell you what words in your document are the most important words. And it does it basically by this, by applying this right here. And it's not simply dividing, you're actually dividing by the number of documents over the number of documents containing the term I. So that's what TF-IDF is. It's rather simple, and I didn't do a good job of explaining it here, but it's simple and it's been used a lot. It's useful when you don't know really how many topics you're going to get. All you need to know is what are the really important words that are in your document. So let me see if there's any other questions on chat, and you're welcome to open your microphone. I haven't heard anybody, so I don't know if your microphones are on. I'm going to go back.
Yeah, thank you, Ben. There is no other questions so far in the chat, but
okay.
No, yeah, but if any of you have anything else that you want to ask Ben, now is the chance. And of course, you can ask later if there is something else comes up.
Yeah, we know it's late, so thanks for sticking out.
Yeah, thanks for sticking in there, and we'll put the recording up later. And if you have, Clay, what do you want people to do if they have questions on the recording? Can they? It'll be a YouTube video. Can they ask on YouTube?
Well, we're
on Discord. Yeah.
Yeah, we're going to publish on YouTube, and then it will also be available on Discord. So if you have any questions about it, if you view it, then yeah, you can ask it there.
So as you know, I'm having a little trouble with Discord. Maybe if you, Clay, if you see questions on there, let me stop sharing now. If you see questions on there for me, could you relay them to me?
Yes.
Yeah.
Absolutely.
Okay. Thanks.
I'd be happy to. Yeah.
Yeah.
But yeah, I guess that's it. Ben, thank you very much.
Yeah, sure. Al, you know me, I can talk a lot about these kind of things.
And Abhishek and Tushar, thank you so much for being here, even though it's already 3 a.m., I believe.
Are you in India? Is that Tushar? Is that where you are? Oops.
Yes.
I think you went to sleep.
No, he said yes in the chat.
Oh, he did. Oh, I'm sorry. I'm sorry. Okay. Okay. Thanks for staying up. Thanks for staying up to listen. Tell your friends to go to YouTube and hear it again and ask questions.
Yes, absolutely. Okay. Perfect. Thank you, guys.
Okay. So the next thing is at 3, right?